Hi everyone. Today's lecture is Develop Matrix Model for TECO, CLM, and OKD. The goal of today's lecture is to understand what is the matrix version of carbon models, be able to write a matrix carbon model, and for advanced participants, to think about potential applications of the matrix model for your own research. Instead of write down the carbon balance equation one by one, as shown here, we could also summarize all of those carbon balance equation into this one matrix equation, which captures the carbon balance for each of the carbon pool and also the interactions between carbon pools. One thing to keep in mind is that this matrix version of this carbon model is mathematically identical to the original carbon model with regard to the carbon dynamics. Let's have a look at this matrix version of the carbon model. In this example, I have the rate of change of the carbon pool size in the left-hand side of the equation. Depending on how many carbon pools you are tracking for your system, if you have, for example, 7 carbon pools, X here is a column vector with 7 rows. The right-hand side of the equation captures those incoming and outgoing fluxes we have been talking very frequently. B here is the allocation matrix, which functions to allocate the external carbon input I into different carbon pools. You could think I as the photosynthetic carbon input. B captures the fraction of photosynthetic carbon that is allocated into different plant organs. X here is our state variable, that is the carbon pool size. K here is the potential turnover rate matrix. Kc here is the environmental vector matrix that modifies the potential turnover rate. A is the transfer matrix, which is n by n dimension. And here is the number of your carbon pools. A matrix captures the fraction of outgoing carbon flow from one pool that is being transferred into a second pool. From the location and sign of the elements in a matrix, we could reconstruct the network of carbon transfers among different carbon pools. Here is an example after expanding these matrices of the TECO model. B and X here are 7 by 1 vectors. A and K here are 7 by 7 matrices. K is a diagonal matrix with each of the diagonal elements, the small k's, corresponding to the turnover rate of each of the carbon pool. The diagonal elements of the allocation matrix are all -1. Those non-zero elements of the off-diagonal component of the A matrix correspond to the fraction of carbon flux that is transferred from the I's to the J's carbon pool. The I here is the column number and J here is the row number. For example, here I41 in the first column and fourth row tells us that there are carbon flux that is transferred from the first carbon pool. Here is the phonage to the fourth carbon pool, the structure liter carbon pool. Actually, all of those transfers in this carbon flow diagram are mapped in this A matrix. As I mentioned earlier, this matrix version of the carbon model is especially handy if we have many carbon pools in our system. Here is an example of the liter and soil organic carbon component of the CLM 4.5 model with 70 carbon pools and the OKD mixed model with 100 carbon pools. The matrix equation for CLM and OKD mixed looks very similar as the matrix equation for TECO. Here we have one more item, the V matrix, which captures the vertical transfer of carbon between the adjacent soil layers. Actually, in the A matrix, The transfer matrix here is more complex than earlier case. Since both CLM and ORCHIDEE MICT assumes the fraction of carbon transferred between different types of organic matter is the same for different soil depths. So I construct the A matrix as a block matrix, which means A is made up by smaller matrices, that is the block. For CLM 4.5, each smaller block, for example, the A31 here, is a 10 by 10 matrix corresponding to 10 soil layers. The diagonal elements of the A31 are actually the same since the original model assumes the fraction of transfers do not change with soil depths. For ORCHIDEE MICT, it is actually a little bit more complex, as neutral pool here in this model are not differentiated by soil depths. So for transfer of neutral carbon flux to soil carbon flux, for example, A51 here, they are 72 by 1 vectors. Well, for transfers among soil organic carbon, for example, A65, they are matrices with 72 by 72 dimension. Here, A65 means there are transfers from 72 active soil organic carbon pools to 72 small soil organic carbon pools. So based on those examples, we see the matrix equation for different carbon models may take a similar form, but the structure of each matrix might be different. How each of these matrices in this equation is organized actually depending on the original model. Each element of this matrix might be parameterized as a simple parameter, and it might also be constructed as a very complex function depending on how the original model represents those relevant processes. After we get to know how the matrix looks like, next step is to derive the matrix model from the carbon balance equations. Here I take the ORCHIDEE model as an example. I assume we have I1, I2, I3, I4, 4 inputs for each of the neutral carbon pool. Carbon from the neutral carbon is transferred into different soil organic carbon, and there are internal transfers among different soil organic carbon pools. Here is the carbon balance equation as we introduced earlier. Here is the matrix equation. The matrix X is easy to construct. We put the 7 carbon pools, that is X1 to X7, to a column vector. I here is the input vector with I1 to I4 as my input rates for neutral carbon pools, and 0 for soil organic carbon pools, as these pools receive no external carbon input. The key in the decomposition rate matrix is a diagonal matrix with each element corresponding to the potential turnover rate of the corresponding carbon pool. Now, the transfer matrix, the A matrix, is a little bit difficult to construct. I will talk more in details in later slides. So if we combine this key matrix with this X, we will see these K1, X1, K2, X2, etc. So the transfer matrix, the A matrix, functions on these K1, X1, K2, X2, etc. By the rules of the matrix multiplication, a n by n matrix multiplies a n by 1 vector, that is A multiply the Kx, will produce n by 1 vector. The value of the ith row of this multiplication equals the sum of the products between the ith row and the column vector. So let's take the 6th row as an example. So the result equals the sum of the products between elements of this row and this column. That is 0 multiply K1 X1 plus 0 multiply K2 X2 plus F63 multiply K3 X3 plus F64 multiplies the K4 X4 plus F65 multiply K5 x5 minus 1 multiply K6 x6 plus 0 multiply K7 x7. That is exactly the carbon balance equation for our 6-carbon pool. If we look into each column of the transfer matrix, the A matrix, it summarizes all the fluxes that is transferred out of the ith carbon pool. For example, if we look into the 4th column of the transfer matrix, there are carbon transferred from the 4th to 5th and from the 4th to 6th carbon pools. If these parameters, the F54 and F64 are not equal to 0, which is exactly the same as we have been shown here in this carbon flow diagram. If we summarize all those off-diagonal elements in one column, here for the 4th column, they are F54 plus F64. If this value is smaller than 1, that means there are carbon lost out of the system. Here is mostly likely the CO2 through respiration that we do not track further. If we look into each row of this transfer matrix, it summarizes all the carbon fluxes that are transferred into this carbon pool. For example, if we look into the 6th row, we have F63, F64, and F65 as the non-zero and non-1 elements. Then I know there are fluxes from the 3rd, 4th, and 5th carbon pools that is transferred into the 6th carbon pool. Let's have a check on this carbon flow diagram, and I highlighted these transfers in yellow. If we follow the rules of matrix calculation and expand this matrix equation by row, we should get the exact carbon balance equation we wrote earlier based on the carbon flow diagram. After you get familiar with the matrix calculation, you would be able to say the matrix equation covers all the information from the carbon flow diagram and the carbon balance equations. We have only one matrix equation, where the detailed information is folded into different components of these matrices. Next, I'm going to explain a little bit more on this model with vertical soil layers. Now is one more matrix, the vertical transfer matrix, V matrix here. The X matrix, the K and I are generally constructed in the same way as we did earlier. The transfer matrix, the A matrix, with 100 by 100 dimension, is folded into this block matrix. Each of the smaller block is in black. For example, A51 is a depth-dependent vector which tracks the fraction of neutral carbon that is transferred into soil organic carbon in different soil layers. These A matrices in right are 72 by 72 diagonal matrices that captures the transfers between different soil organic carbon categories in the same soil layer. Each item of this diagonal takes the same value as ORCHIDEE mix assumes the transfer fraction are not depth dependent. The vertical transfer matrix, the V matrix, can be represented by this block matrix. As you can see, most elements in this block matrix are 0, except those for active, snow, and passive soil organic carbon. I will take the snow soil organic carbon as an example. The vertical matrix is actually a tri-diagonal matrix with the lowercase number indicating soil layers. H and G correspond to the mixing rate between the current and the upsoil layer and between the current and lower soil layer. For people who are interested in those details, you could refer to the reference I cited here. And thank you.